Right. So I wrote these notes originally so that to overcome the problems with the Blackboard, but now there is, it seems, brand new, almost brand new Blackboard here. So I guess you don't have to follow the notes anymore. I'm going to start with a lightning recap of yesterday's discussion, the second part of yesterday's discussion. And if there are any questions about what we've been discussing yesterday or about the general goal, please stop me. So we discussed the fact that in 3 dimensions, well, in any number of dimensions, but particularly if you have a flat 3-dimensional space, then you can map it to a sphere by the stereographic map, the Common Stereographic Map. And this is a conformal map. And this algorithm provides you with a way of compactifying conformal field theories on spheres. So we can compactify CFTs in 3 dimensions on S3. So there is a canonical, in some sense, map from a flat space to the sphere, which allows you to put conformal field theories on the sphere. Then we discussed the partition function for the sphere. Actually, the log of the partition function minus the log of the partition function. And that generally, that's generally a divergent object. If you just compute it tabula rasa, you'll see that it's divergent. We'll do some computations along these lines today. That's generally a divergent object, and it's given in terms of the radius of the sphere. So there is a cubic divergence, then there is a linear divergence, and then there is a special guy, which I called F. F is an observable of the continuum theory. It does not depend on the regularization scheme. These divergent terms can be cancelled by local counter terms, which are correspondingly the cosmological constant term and the Einstein-Hilbert term. So F, while F cannot be cancelled by any local counter term, and F is a property of the continuum theory. So you can compute, given a specific conformal field theory, you can compute F. And the conjecture that's been put forward in the last year is that F UV in absolute value is always bigger than F infrared in absolute value, where UV and infrared refers to 2 conformal field theories defined at short and long distances. So if you have a flow from some conformal field theory in the ultraviolet to some conformal field theory in the infrared, this inequality should be satisfied according to the conjecture. The fact that there is no local counter term that can cancel F is slightly non-trivial, but it's true. And also there is another subtlety here that F may be complex in general. So for theories which are non-parity invariant, F would be generally complex, and then you need to take the absolute value. That's what the conjecture advises us to do. Anyway, so are there any questions about this conjecture? Yes?
Do you expect it to be peculiar to 3 dimensions or to all odd dimensions?
All odd dimensions. Perhaps above some number of dimensions, there aren't really interesting flows, but in 5 dimensions, there are definitely some interesting flows. So that should be true also in other odd dimensions. OK, so that was where we stopped yesterday. Today, I'll tell you, we'll go through one example of calculating this F. Then I'll show you one amazing fact about this conjecture. A spoiler is that this conjecture is somehow a natural generalization of Zamolodchikov's theorem from 2 dimensions, in the sense that it tells you that the number of degrees of freedom decreases along G flows, corroborating our intuition that we integrate out massive particles, even though this intuition, as I mentioned, is not really correct in any sense, but it somehow corroborates this raw intuition. What I'll show you today, among the examples, is that in fact there are topological theories in 3 dimensions that no normal person would associate any degrees of freedom to, but F is non-zero. And it's extremely important that F is non-zero for this conjecture to be true. So if you have even a topological sector in your theory, you should take into account its contribution to F. You'll see that that's highly non-intuitive, but it seems to be crucial for the many, many tests that this conjecture passes.
Did you say it's the same about C theorem in 2
No,
dimensions?
in the C theorem in 2 dimensions, C is 0 for topological theories in 2 dimensions. It seems very peculiar and confusing, maybe non-intuitive, that F is non-zero for topological theories. But for topological theories, so even for topological theories, the partition function on the sphere may be non-zero, as you'll see. And sometimes the topological sector of the theory contributes to this measure of the number of degrees of freedom F much more than the dynamical degrees of freedom of the theory. And this, That could be, yeah, it's related to, in some sense, the number of the ground states of this theory, but these theories have no propagating degrees of freedom. So that's in some sense goes in the same way that I was trying to tell you in 2 dimensions, that this intuition of losing degrees of freedom is not really what's going on. I mean, it's somewhat correct, but it's not the true, it's not the whole story. And this example is, yeah. So this example is examples in 3 dimensions, as you'll see, are highly dependent. The fact that this is true in all the known examples is highly dependent on the fact that you take into account correctly the topological sectors of the theory.
Wait, one question. I don't think I missed any of your lectures. When you talk about the normalization group flow, you never actually defined it. You're thinking of something like the Polchinski equation?
Well, so the renormalization group flow takes place in flat space. You start from a conformal field theory in the ultraviolet, you add the relevant operator, and you flow to a conformal field theory at long distances. This is Wilson. You just do whatever Wilson told us. You just go, I mean, at short distances, there must be power laws. Just because at short distances, you cannot have anything else. Yes?
But if you want to describe it in terms of the equation,
yes.
it's something like Polchinski's equation.
It could be Polchinski's equation, but that's not, yeah.
Well,
Oh, I don't think it's necessary. I mean, all I'm requiring is that there is a physical theory. Imagine a condensed matter theory.
so maybe in many ways, many procedures.
That's right. But the point about this conjecture is that it's a statement about the deep UV and the deep infrared. So it does not actually depend on what you do in between. So once you have a given flow, that's right. The conjecture is about F. So F is associated to this conformal field theory, and this F is associated to this conformal field theory. So, and then the conjecture is well defined. Of course, the dream is that eventually when these things are understood, there will be a natural way to extend it somehow along the flow. But now the conjecture is about the edge points of the flow, which are well defined physically, regardless of the procedure itself. Yes?
Indeed topological theory, you wouldn't expect that it will change, right? Because I mean, it's
You'll see. I'll give you examples. Okay, so just to warm up, I'll show you how to do computations like that, and that would be quick. I'll do a free scalar. I already told you what is the value of f for a free scalar, and I'll just show you what goes in, how the computation goes about. So a free scalar is a well-defined theory in flat space. It's a conformal theory, obviously. And there is a canonical way to map the free scalar to the sphere, as I said. When you map the conformal scale, when you map the scalar to the sphere, you need to introduce something that's called a curvature coupling. I'll tell you why that is needed. So we have a half, and then we have, this is already on the sphere. So we have a square root of g. So that's what you get when you map a free scalar to the sphere. You get, of course, the kinetic term for the scalar. And then there is this peculiar curvature coupling, which is in 3 dimensions 1/8 times the Ricci scalar of the sphere. So this is the Ricci scalar of the sphere, which is just a number. It's 6 over the radius of the sphere squared times phi squared. So you see that when you take a free scalar and you map it to the sphere, you get this kind of mass term on the sphere. That's necessary in order to maintain Weil invariance on the sphere. So to maintain a Weil invariance on the sphere, because this guy spits out some inhomogeneous factor, you need to add the Ricci scalar here that would compensate for the non-Weil invariance of the kinetic term itself. So if you want to repeat this exercise and see where this comes from, you should think about this in a general background metric, G, not necessarily the sphere. And then the transformation which necessitates this term is the familiar Weil transformation, which is just the same thing as a conformal transformation. So these are the Weil transformations of the field and the metric. And to preserve Weil invariance, you need to add, on a general manifold, you need to add this Ricci term, which of course vanishes in flat space. But on the sphere, this is a constant, so it needs to be included. Okay, so the idea is to compute the partition function of this object, and that you do, because it's a quadratic theory, that you do quite easily. So you do that by by writing, of course, that minus log of the partition function is a half of the logarithm of the determinant of the Laplacian squared plus 1/8, the Ricci scalar on the sphere. And then what you need to do is to solve for all the eigenvalues, all the eigenfunctions of this Laplacian plus r, and count the multiplicity. It's important to count the multiplicity, and then take the product, take the logarithm, and so on. So the eigenvalues of the Laplacian on the sphere are given by 1 over the radius of the sphere times n plus 3, and then n plus 1/2. So these are the spherical harmonics on the sphere, and the multiplicity of the nth eigenvalue, so they're highly degenerate, is n plus 1 squared. So there is a huge multiplicity for these guys. And now you just multiply all these eigenvalues with the correct multiplicity and sum them up. That gives, so what you get is that this sum becomes, so this equality, this log, a half of the log of the determinant becomes a sum from 0 to infinity minus 2 log of some, well, mu naught is some cutoff that you introduce, some scale that you introduce to keep track of the dimensions. There will be no dependence on the scale eventually. A plus log of n plus 3/2 plus log n minus 1/2. So you see where all the terms come from. Of course, they're all multiplied by the multiplicity. So the fact that there is this multiplicity multiplying everything is trivial. Then you see that n plus 3 is basically this log, and my n plus 1/2. Sorry. Yeah, this, I have a small typo here. Oh, I think it's plus 1/2. So the log n plus 3 comes from here, n plus 1/2 comes from here, and 1/r², which is the radius of the sphere, sits in this logarithm, and this is why there is a factor 2, and mu naught is just something to soak up the dimensions. That will go away eventually. Yes? All right, so now this sum has to be computed. It's obviously a divergent sum. You'll see that it's diverging because this thing doesn't decay fast enough. It's a logarithm of n, so it diverges kind of linearly. But nicely, if you do a zeta function regularization, the sum over dmn, so the sum over n plus 1 squared with a zeta function regulator is 0. So there is no dependence, no logarithmic dependence on the radius of the sphere. This is the crucial difference from 4 dimensions. If you repeated this calculation on the nose in 4 dimensions, the sum over the multiplicities, when regulated with a zeta function regulator, would be non-zero. And then this piece, which depends logarithmically on the radius of the sphere, would not drop out. But the zeta function regulator forces one to set the sum over n plus 1 squared to 0. So there is no logarithmic dependence on the radius. And then you get, with this zeta function regulator, some finite contribution from these guys. The formula that one gets with a zeta function is that this is minus 1/2, the derivative with respect to s, where s is some parameter in the zeta function that you'll see. Then you get twice the Hurwitz zeta function, s minus 2, 1/2 plus 1/2 zeta s 1/2. Okay, so this sum can be regulated with this zeta function prescription, and this can be computed. You just go to your favorite database for zeta functions. You compute this derivative at 0. This derivative is evaluated at 0. You compute it, and you get the formula that I already quoted yesterday, which is 1/16, 2 log 2, minus 3 zeta 3 over pi squared. So this is the contribution to this count of the number of degrees of freedom of a single scalar, which is roughly 0.6. Okay, so this is how it goes for bosons. For fermions, the exercise is similar. I already quoted the result yesterday, so I won't go through it again. So now, if you have some theory with NF bosons and NF fermions, you can calculate this F, and then you can start deforming this theory. Yes?
So it's kind of interesting, these numbers, because fermions usually twice scalars.
That's right.
Here, each term is a factor of 2, except for the sum.
Yeah. So sorry, there was a typo here. Can you say exactly? Yes.
Instead of 2 over 16 for fermions, you have 4 over 16. Instead of 3 over 16, you have 3 over 8. Except for the sign, it would be again a factor of 2.
Mm-hmm.
So for some reason, there's a factor of 2, and then there's a minus the plus.
Yeah, I think that this. Yeah, the minus flips its sign. Yeah, you see that.
The first term doesn't.
That's right.
It's a factor of 2.
Yeah, but even when you calculate the free energy, the fermion doesn't give you twice the result for the scalar. And Nima reminded me yesterday that a fermion in 4 dimensions gives 7 over 8. Yes, in 2 dimensions it scales nicely, and as you would expect. But even the free energy, which is some other way of counting degrees of freedom, does not scale in the naive way. The free energy of a free fermion is like 7 over 8 in 4 dimensions. Yeah, this is a very mysterious formula, indeed. And now I'll get to the more bizarre thing, which is that I'll explain why even topological field theories contribute to F, and I'll give you an example where this contribution is important. So that's the most amazing part about this conjecture, probably. Yes?
And that is F term for ultraviolets, or what do you calculate just now?
This is the F associated to the conformal field theory of a free scalar. I didn't tell you whether it's the infrared or something, or the UV of something. I did not deform it yet. If you wanted to deform it, you would add this theory, and you add a mass term. Then it flows to an empty theory, right? And then you get an obvious, this inequality is obviously satisfied because this is positive, and the infrared is an empty theory.
It's not like I have this here, then I add here masses.
I did not yet add masses. This is the free scalar. If you wanted to deform the free scalar, the infrared conformal field theory would be empty.
Up to topologies.
Up to topologies, but for a free scalar in 3 dimensions, there is no topological term in the infrared. So for this case, the infrared field theory would be empty, and the inequality would be obviously satisfied, because F in the infrared is 0, and F in the UV is 0.06. Okay? Oh, there's something about the eraser. Right. So now I'll tell you something about Chern-Simons terms, which is a whole topic by itself. And this, what I'm going to tell you, has been computed by Witten in his seminal paper about Jones polynomials, for which he got the Fields Medal. So it's not my purpose to review this paper because it's highly technical, and I'm gonna just give you some bits of intuition and quote the result. So the Chern-Simons theory in 3 dimensions has no propagating degrees of freedom. The Lagrangian is k over 4 pi, where k is called the Chern-Simons level. And then on a generic manifold M, you write trace A wedge dA plus 2/3 A wedge A, where A is the gauge connection for some gauge group G. So this is associated to some gauge group G, associated to G. And so this is the Chern-Simons section. You know that it's topological. The metric does not appear anywhere in the Lagrangian. It's a purely topological term. And the equations of motion of this theory are given by varying the action with respect to A, which means that F mu nu has to be set to 0. So when you vary this action with respect to A, you get the equation that the connection A has to be flat. So the only configurations that contribute to the equations of motion are flat connections. And since these equations are first-order equations and not second-order equations, they do not describe propagating degrees of freedom. They describe some isolated sets of gauge field configurations which are flat. So these are some sections of the gauge bundle which exist globally on the manifold M, and there is an isolated set of them. In fact, there is a theorem in mathematics that the space of flat connections is in one-to-one correspondence with homeomorphisms from the group pi1 of M to G. So there is a one-to-one correspondence between the space of flat connections and homotopy classes of isomorphisms between the fundamental group and the gauge group. Basically, the intuition is that for every cycle, you can stick a Wilson line. So these are the flat connections. So you count how many cycles there are, and this is more or less the number of flat connections. So this is an isolated set. It's a finite thing, and yet this contributes to the count of degrees of freedom in 3 dimensions, and it's extremely important that it's there, as I've already emphasized. So what Weizmann did in his seminal paper is that he computed the partition function. So he computed the partition function of the Chern-Simons theory on the 3-sphere. What he found is that this f, so now I'm switching to my f, the number of degrees of freedom. So Weizmann found that for U1 Chern-Simons term at level k, the result is a half of the logarithm of the level. And this is by itself shocking, because you see that if you take a Chern-Simons theory, a U1 Chern-Simons theory with a large level k, it contributes more than any number of fermions or scalars. Well, it's logarithmic in k, but still, you can have, for large enough k, it could contribute more than a fermion or a scalar. For an SUN gauge theory, well, for UN gauge theory, Weizmann solved this problem too. This is the famous formula that he obtained. If you take f of a UN gauge theory at level k, then there is a formula which reads n/2 log of k plus n. And then there is this sum that you've probably seen in many places, n minus j. It appears in many places in mathematical physics. Log of twice the sign pi j over k plus n. So there's and j runs from 1 to n minus 1. So Weizmann computed this partition function of the Chern-Simons theory for every k and every n, and any manifold m, basically. But for the 3-sphere, this is the result. This result is highly non-trivial. You have to be careful. You have to solve this path integral exactly. In some sense, this theory is integrable, which is why Weizmann was able to do what he did. And so you see that basically this contradicts the raw intuition that there is that f counts the number of degrees of freedom. F receives a pretty large contribution even from Chern-Simons terms.
Doesn't this remind a little like what Amit said yesterday about the linear dilaton? Because it seems like you can take infinity from a U1 gauge theory.
A U1 gauge theory which is topological.
Yes, which looks ridiculous. Like it looks that you can take with a linear dilaton and a real infinity because of that term.
Yeah, it does. Yeah, it does sound somewhat reminiscent. Yeah, but in that case, C is definitely 0 for topological theories. And the crucial thing here is that F is non-zero for topological theories. Right, so now I'll take you through one example, which is the most basic example where this F theorem can be tested. And then we'll get to something else. All right, so the simplest example is to take a UV fixed point, which consists, so our UV fixed point, now we'll consider a non-trivial flow. So the UV fixed point is a U1 Chern-Simons theory with level k, plus an F fermions, an F Dirac fermions in 3 dimensions. So if you just write the minimal Lagrangian, if you write a bunch of fermions in 3 dimensions, coupled minimally to the gauge field, and you add a U1 Chern-Simons term at level k, then you get an automatically conformal theory. This theory is automatically conformal because there is no continuous coupling in this theory. So there is no coupling that can run. The wave function for the fermions can be swallowed by redefining the fermions, and the Chern-Simons level is quantized by gauge invariance. It's quantized to be an integer. So there is no candidate for running coupling in this theory. Indeed, this theory is conformal. You can check it in perturbation theory, where this theory is weakly coupled. So this theory is the UV fixed point, and now we add masses. So now we add masses for the Dirac fermions. Okay? Now in the infrared, the Dirac fermions are to be integrated out. This theory is no longer conformal, and it flows to some other fixed point. The other fixed point, so this is the UV fixed point. After you've added the masses, these Dirac fermions are integrated out, and they flow to a new fixed point. The fixed point, of course, includes no propagating degrees of freedom, because the only propagating degrees of freedom in the UV were the Dirac fermions, and now I've given all of them a mass. However, when you integrate out the Dirac fermions in 3 dimensions, you generate Chern-Simons terms. So the infrared fixed point is in fact empty. But it contains a Chern-Simons term at level k plus minus n, nf over 2. So the plus minus is dependent on whether the sign for this mass of the Dirac fermions is positive or negative. So the sign of the Chern-Simons term level in 3 dimensions is linearly proportional to the sign of the mass that I'm putting for the Dirac fermions. So in 3 dimensions, there is a difference between positive and negative mass, and it affects the Chern-Simons level with a plus minus, depending on the convention for the mass.
Let's do the following paradox now. Let's add both masses with both signs, so there is no parity violation.
Yes.
In that case, you won't generate the Chern-Simons.
That's right. There is no, that would not be a contradiction. That would be even easier to satisfy. You'll see. So the conjecture here. If the conjecture is right, it means that the partition function of the UV fixed point is larger than the partition function of the infrared fixed point. The infrared fixed point is, strictly speaking, from a field theory's point of view, empty. But you saw that this f is quite subtle, and you have to keep track of Chern-Simons terms. So the conjecture would amount, in this case, to saying that a half of the log of k plus minus nf over 2 is smaller, and this is the crucial sign here, smaller than the contribution from a Chern-Simons term at level k, which is a half log k, and the contribution of an f Dirac fermions. This formula on the right-hand side is in fact approximate, because this is an interacting conformal field theory. But when k is large, this theory is almost weakly coupled, and the partition function in the UV is the sum of the partition function of the Chern-Simons term and the NF Dirac fermions. So this formula is exact in the infrared, but this formula only holds when k goes to infinity. When NF goes to infinity. K much bigger than 1, and well, it's probably enough just to send k to be very large. Yes. Yeah, so this formula would be right when k is much, much bigger than 1. When k is much, much bigger than 1, the UV fixed point can be treated in perturbation theory, and therefore the partition function is approximately the sum of the Chern-Simons contribution and the Dirac fermions. There are corrections that nobody knows how to compute. Well, nobody can tell you a closed form formula for this theory, I guess. But in principle, this is the formula for large k. So we get a half log k plus nf with the contribution of 3 fermions, which is this formula that I've given you yesterday, 8 pi squared. So if the conjecture is true, this inequality has to be satisfied at large k and a fixed nf. And indeed, you can check that this is true in the regime advertised. So this is a non-trivial check of this flow. It's a non-trivial flow, and this is satisfied. There are many other checks. There are tens of papers by now with many different checks of this F theorem conjecture. I would not go through all of them. Of course, they're more or less the same conceptually, but many of them are highly non-trivial, and they come close to saturating this inequality. But in every single example, they end up satisfying the inequality as they should. Yes. Yes. Now the next step is, of course, to generalize U1 to SUN, and people have studied that too, and you can see that it's satisfied. So this was just one example to tease you, I guess, that it's satisfied in a pretty non-trivial way, an interesting way. So now I'll go to something which is more interesting and also connects to many other developments in field theory in the last few years. So in particular, this conjecture about the F theorem is something about the partition function on the sphere. So one idea that has been pushed in the last few years is to study supersymmetric theories on spheres. If you study, and it turned out that you can compute the partition function of supersymmetric theories on the sphere exactly by a method which is called localization. Then this framework provided many consistency checks of this proposal, and also many other applications stemmed out of this study. So what I'm going to do now is, keeping this in mind, I will go through the formalism which people developed in the last year or two for putting supersymmetric theories on curved manifolds. That by itself is a huge field, and some people in the audience I know are working on this problem right now of putting supersymmetric theories in curved space. I'll tell you what is known more or less about this three-dimensional three-dimensional theories in curved space. And I'll show you that in these theories, you can compute the partition function of the theory exactly. Even for theories which are inherently strongly coupled, one can compute the partition function of the theory exactly. And therefore, many checks of this kind for the F-theorem and many other conjectures follow rather easily. So now I'm switching basically to a somewhat different topic, but of course motivated by all of that, which is supersymmetry in curved space. The connection between that and what I'm going to discuss now is that in the end, you'll see they compute essentially the same quantities. So supersymmetry on the three-sphere. So from what I'm going to say, you'll see that there are many open problems in the field that are still not addressed, and many people are working on them, and there is a lot more to be contributed. So I'll discuss n equals 2 supersymmetric theories in 3 dimensions. N equals 2 in 3 dimensions is the same as n equals 1 in 4 dimensions from the point of view of the number of supersymmetries and the way the superspace looks like. So there is the usual holomorphy that you heard from Michael Dine, and some of you probably knew from before. So n equals 2 3D is very similar to n equals 1 in 4 dimensions. The supersymmetry algebra in flat space is QQ equals to 0, which is also equals to Q bar, and then Q with Q bar. So in 3 dimensions, there is only one spin or index. There is no dotted spin or index. So Q with alpha with Q bar alpha beta, is given by the momentum P alpha beta, where alpha and beta are symmetrized. The momentum, which is a vector, can be written as a symmetrized object in the spinor indices. Then there is also a central charge in 3 dimensions, but this central charge will be completely immaterial for what I'm going to discuss. So this is the supersymmetry algebra in 3 dimensions, n equals 2 supersymmetry algebra. It's pretty standard, and nothing fancy about it. And now the big question that I want to raise, and I encourage all of you to think about this question in some generality, and many people are doing that right now. The question is that given that this is supersymmetry in flat space, it's manifestly in flat space because we have the translation operators here. The translation operators make sense only in flat space because this is a flat, well, this is the only manifold up to conformal transformations on which you can define such Killing vectors. So the problem in general that I want to address, and I won't give you a solution to this problem because the solution is not yet known, but the problem is how to study, are there supersymmetric theories? So are there SOSI theories on curved manifolds? Curved manifolds, which I denote by the letter M. So the big question is, can you write a supersymmetric theory on a curved space? That does not have, you should be careful not confusing this question with the question of whether supergravity theory exists. Supergravity is a different notion altogether. Supergravity is not just a global supersymmetric theory. It's not a rigid supersymmetric theory. In supergravity, supersymmetry is gauged, and diff transformations are gauged, and so on and so forth. That's a completely different ballpark. I'm talking about globally supersymmetric theories with no dynamical gravitons, no dynamical gravitinos, just ordinary theories of fermions and bosons and gauge fields, which are supersymmetric on curved manifolds. There has been a lot of interest. There has been a spurt of interest in the recent years in this question because people found that many mathematical physics questions arise naturally when you compute various quantities in supersymmetric gauge theories on compact spaces. You can address even very physical questions, like the question I'm discussing here about RG flows and inequalities and the loss of degrees of freedom, that is very tightly connected to such constructions. So there seem to be many motivations of studying these questions. Mostly they're in mathematical physics, but some motivations are like what I'm talking about, which is definitely old-fashioned physical field theory. So there are 2 approaches to solving this question. None of these approaches has been pushed so far to the most complete form it could take. But some people did partial work on both of these approaches. So how would you study putting a supersymmetric theory in curved space? One approach of putting a supersymmetric theory in curved space is to say, we start from the flat theory. We start from the theory in flat space. We know what are the fields. We know what are the transformation laws. We know what is the supersymmetry algebra. And we just bludgeon through the equations, and we try to add terms which go like 1 over volume of the manifold. So we just force the theory to admit new terms, which go to 0 when the volume of this curved manifold goes to infinity. We try to brute force, to do some brute force calculation, adding these terms, and fixing the supersymmetry algebra at the same time. So you have to fix the supersymmetry algebra, you have to add new terms to the action, which vanish when the volume of the manifold goes to infinity. So you have to do a lot of work. And in the end, if you are lucky, this procedure will close. So at some point it will terminate, and you'll have a finite Lagrangian with finitely many terms beyond the flat space Lagrangian. It could also be, logically, that it would never terminate, that you would have to add terms with an arbitrary negative power of the volume of the space, and that's the only way to close the supersymmetry algebra. For some reason that is not yet understood, it seems very similar to what happens in gauge theories. So in gauge theories, when you add gauge coupling, you have to force a Siegel term into the problem. The Siegel term takes care of the fact that when you add the gauge coupling, you violated gauge invariance at order g squared. But once you add the Siegel term, everything closes. You don't need to add any further couplings. It seems similarly, in this problem, it seems from many examples that people have studied, that you basically have to add to the flat space Lagrangian only 2 terms. One that goes like 1 over the volume, and one that goes like 1 over the volume squared. And then it terminates. So it seems that there is a unique Siegel term, which you can think about this 1 over volume squared guy as a unique Siegel term that you need to add, and then the whole algebra closes. You can write transformation laws. By what?
Any arbitrary space with no isometry.
The answer is not known, but for a class of manifolds which people studied, this turned out to be true. People studied the spheres, ellipsoids, orbifolds of spheres and ellipsoids. And they all have some isometries, yes. And then it terminated. I think I would expect that for a general manifold, that would be the structure. I would expect that that's the answer in general, yes.
One supercharge.
With 4 supercharges. With 1 supercharge, it may be more. Yeah, for n equals 2. I'm talking about the supersymmetric theories with 4 supercharges, n equals 2. Right. Yes, so with n equals 2.
Your expectation would be that for any manifold,
Yes.
something would remain.
No. So there is only a limited class of manifolds for which you can put supersymmetry on. Yeah. I'll talk about it. So there is a limited class. For this class of manifolds on which you can put supersymmetry, I definitely do think. Yes, I'll talk about the conditions in a moment. So yeah, I do expect that for the manifolds which admit all the conditions that I'll mention in a moment, that would be the final answer. So to couple a flat space theory with this power of 1 over the volume, it's quite straightforward because this is given by the energy momentum tensor. So this is basically a linear coupling to the background, and you know how to do that, and then this can be interpreted as a Siegel term. And in examples that people worked out, this is where it terminated. And then you can compute all the transformation laws, and so on and so forth. Of course, as David said, not on every curved manifold you can put supersymmetry consistently. In many manifolds, if you try to follow this procedure, by the way, you can call this procedure the Netter procedure. Well, this is what people used to do in the past in supergravity and so on. So if you follow this Netter procedure to its exhaustion, you'll see that you get constraints on the manifold M. Not on every manifold N can you put supersymmetry. You need something like a covariantly conserved spinor. That is quite intuitive because if there is no covariantly conserved spinor, there is no meaning to supersymmetry. However, I put this condition in quotation marks because the correct condition turns out to be much more complicated. It's not what mathematicians call covariantly conserved spinors. When you follow this procedure, you get some horribly complicated algebraic equations that are somewhat similar to a covariantly conserved spinor, but they are not. So these are new equations in mathematical physics that many people, including some in the audience, are now working on solving. So it's not known yet what is the full classification of the manifolds, and it's not yet known, as far as I know, what is the general solution of this problem. Yes?
But you have to make sure you can put fermions on top.
Yes, you need to be able to, yeah, you need to have sections of the spin bundle and so on and so forth. You need an orientable manifold, that's obvious. And then there's, well, any orientable manifold in 3 dimensions is also parallelizable. So it's pretty easy to, well, the mathematics is not horribly complicated, but the equations that you get, surprisingly, are not a covariantly conserved spinor. They're not, by no means. These equations are much more complicated, and nobody knows what the solutions of these equations are yet.
Does that mean that there are solutions that don't, I mean, there are spaces that don't admit covariantly?
Yes, there are spaces which do not admit normal covariantly conserved spinors, which admit supersymmetry.
Or up to, I mean, something like up to gauge transformation or something like that?
No, no,
More subtle?
it's more subtle. There are some experts in the audience. I think they would know even more than I do about this. We can discuss that later.
And the physics, there's no real understanding physically what that extension means.
So I'll tell you from the second point of view, I'll tell you exactly what's going on. What's the physical interpretation of these strange equations? So the other point of view, which is what people actually are pursuing, so I don't know of anybody who actually tried to follow this procedure of doing the netter procedure, brute forcing the equations and forcing the theory to be supersymmetric. The other approach, which I know people are following, is to start from supergravity. And that's a slightly confusing approach, but it's very simple. So bear with me for a second. You start from supergravity. Supergravity contains dynamical gravitons, and it contains dynamical gravitinos. But these people start from supergravity, and they try to force the gravitino to be 0, and the variation of the gravitino to be 0. And they also try to force the variation of the metric to be 0, and the metric to be fixed. So the metric, this fixed metric, is what defines the curved space. Then when you try to force the fluctuation of the metric to be 0, you get some equations. Because to consistently decouple the fluctuations of the metric in supergravity, you need this fixed metric to satisfy the equations of motion. Well, in a physical theory, if you want to decouple some fields, you need to expand around the solution to the equations of motion. So you need to decouple these guys, and you also need to decouple the gravitino. To decouple the gravitino, you also need to make sure that the gravitino equation of motion is satisfied. And you also need, and to preserve some supersymmetry, you also need to make sure that the SOSI variations of the gravitino are 0. Okay? So people are imposing these equations. And these equations in general supergravity are so complicated that on the right-hand side of this guy, you have the equation of a killing spinor, but there are many other contributions associated to various auxiliary fields in supergravity, such as background gauge fields, background tensor fields. So the general equation is much more complicated. It's not just a covariantly conserved spinor, it's a covariantly conserved spinor where on the right-hand side you have various auxiliary fields, like tensors and scalars and so on and so forth. So it's a complicated equation, but people are trying to classify its solutions. So these two approaches are what you should think about. And there is not yet a general solution, and perhaps there is a third approach that I didn't think about, which would lead to the results easily in a more straightforward fashion. So are there any questions about these general strategies? Now I'll just give you the answers for S3. I'll explain why the partition function on S3 can be computed exactly, even for strongly coupled theories. And then we'll draw some consequences for this F theorem. That's the plan for today. So just to give you an example of how such a Lagrangian would look like, I would show you how to put a chiral superfield. A chiral superfield is something that consists of a complex scalar, a fermion, and an auxiliary field. I'll show you how the Lagrangian on the curved sphere looks like. I'll just write it up. So we have d mu phi squared plus I psi sigma d psi plus f dagger f. So this is the first part of the Lagrangian, and you see that it's basically the Lagrangian for a chiral multiplet in flat space. It describes a massless scalar, a massless fermion, and an auxiliary field. And now there are corrections which go like 1 over the radius. The corrections which go like 1 over the radius are r minus a half. I'll tell you what is r in a second. R psi dagger psi plus r 2 minus r. So this is what I promised. It terminates at order 1 over r squared, which is highly non-trivial. Small r is the r charge of phi. So the r charge of phi is small r. That's a choice that you should make. It turns out that to put a theory in a curved 3-sphere, you have to make a choice of what is the r charge of this basic of the fields. This choice is necessary to put this theory in a sphere. And it further turns out that if your theory does not admit an r symmetry, there is no way to put it on the sphere. That's also somewhat surprising, but that's true. So you need to make a choice of the r charge, and you see that the couplings to the sphere depend on the choice of the r charge. In particular, this term contains r minus a half, and if you choose the r charge to be a half, which is the natural choice in 3 dimensions for a conformal scalar, then the first term, which goes like 1 over r, drops. You just get the second term, 1 over r squared. And r is the radius of the sphere. Okay, so this is an example of a Lagrangian, and you can write explicitly the transformation laws for all the fields in the problem. They're written in the notes. I won't repeat them. And the sphere is particularly simple because on the sphere there is a so-called conformal spinor. So the sphere admits a so-called conformal, covariantly conserved conformal spinor. There's an I. And so this is not as arcane as the other examples where there is no spinor that satisfies any familiar equation. So on the sphere, supersymmetry is pretty standard. Yes.
And do we have here while invariant, for instance, that you taught us before that to have a while invariance on the sphere, we have to add something like p squared?
Yes. So yes. That's a very good question, and I'll tell you what's the answer. It's important for what I'm going to say, so I was about to explain it anyway. This theory depends, so to put a theory on a curved 3-sphere, you have to make a choice of the r charge. Theories on curved 3-spheres exist only if there is an r symmetry. This theory is while invariant only if you make a choice of the r charge, which is the r charge of the superconformal field theory itself. So this theory of a free scalar has a U1 symmetry and it has an r symmetry. Only one choice of this r symmetry is the superconformal r symmetry. And if you make that choice, then this theory is while invariant. But if you choose another r charge, it's not while invariant. So r equals a half is a special case. This is the case where this theory is while invariant, because this is the choice of the r charge for which the theory is conformal in flat space. So this is the super.
Charge here relates with the dimension.
Exactly. So this is the conformal choice. In fact, this term, which vanishes, you see that there is a special term that goes away when r is equals a half. In fact, this term is extremely offensive for a field theorist because this violates reflection positivity. So for r equals a half, it's good that you restore the physical interpretation of the theory as a conformal map of a unitary theory that exists in flat space. If r is not equal to a half, this theory does not describe the conformal map of any physical theory in flat space. It's just an isolated theory in the sphere that does not come from a conformal mapping of any theory in flat space. But if r equals a half, you see that the physical interpretation of the theory is restored. It's reflection positive, it's real, and you can interpret it as the conformal map of a conformal theory in flat space. Is that clear?
You mean if we don't have this, the limit in r when r tends to infinity would be the same?
Big R.
Big R.
Yes, the big R to infinity limit is the same. Is the same. But there is another question of whether this theory is the conformal map of a theory in flat space. That's an independent question. Okay? And that's true only if r is equal to a half, because only then a conformal symmetry is restored.
So if you, there's one
This theory admits 4 supercharges. It's an n equals 2 theory. It's an n equals 2 theory on a 3-sphere. There are 4 solutions to this conformal killing spinor on a 3-sphere. Yes. For any r, it admits 4 supercharges. For the special choice of r, it's even superconformal on the sphere. Yes. And unitary. Otherwise, it's not reflection positive. In other words, it's not unitary. However, you'll see that even though it's not unitary, you can compute the partition function, and you can get a lot of physical mileage out of it. I'll show you the trick.
Can you remind why a mass term for
Well, you need an I. You need an I.
With an I, but there's no I.
There is no I. This is why it's a bad thing to write.
So you need, that's
Yeah, there is no I. This is why it's a bad theory. Yes?
I'm surprised R equals half is a special value. It seems also that R equals 2 is a special value. Is there a explanation for that?
No, that's not special value. R equals 2 is... nothing interesting happens at R equals 2. Okay. Right, so now I'll get to some physical arguments which appeared in the last year in the literature, in the last year and a half, about such theories. Before I get to these arguments, I need to tell you what are the transformation laws which preserve supersymmetry in the model that we've just discussed. This is somewhat important for what I'm going to say. It's quite important for what I'm going to say. So I'll just write the transformation laws under these 4 supercharges, picking one, killing spinor. Delta phi is 0, delta phi dagger. You can check yourself later that this leaves the theory invariant. So these are some supersymmetry transformations in flat space, and there are some extra quantities here that I've not yet shown in the Lagrangian. I'll tell you what they correspond to in a second. So there are some dots here which are not important. These transformation laws are not quite of the theory that I've just shown you. It's of the theory that I've shown you coupled to a background gauge field for the U1 symmetry. The theory that I've showed you had the U1 symmetry because the scalar was complex. And you can couple to this U1 symmetry a background gauge symmetry. So the background gauge symmetry, a background gauge field, that would be, the background gauge field is characterized by a gauge field, of course. This is where the gauge field hides in these covariant derivatives. And it also contains a sigma, which is a parameter, well, a gauge field in 3 dimensions consists, a gauge field multiplet in 3 dimensions of n equals 2 supersymmetry consists of a gauge field and some field which is called little sigma. You can think about it as the dimensional reduction from n equals 1 in 4 dimensions, where sigma is just a naught. So I've written the transformation laws not just for the theory that I've displayed, but actually for the theory I've displayed coupled to a background gauge field, meaning to a mu and sigma and some gauginos and fermions that won't bother us. The reason that I'm coupling this theory to a background gauge field will be apparent in a few seconds. Okay, so are there any questions about what these equations mean? There is, in the nodes that I've distributed, you can even find the whole Lagrangian of the previous blackboard coupled to the background gauge fields and fully supersymmetric. I'm just writing these transformation laws for a reason that you'll recognize in a second. So it turns out that because you can couple this theory to a 3-sphere, and you can preserve 4 supersymmetries, you can preserve the full n equals 2 supersymmetry on around 3-sphere, something highly non-trivial takes place. Partition functions on curved spaces are a good object to study, while partition functions in flat space are obviously infrared divergent. They are not very, very physical. Partition functions on curved space, on the other hand, are very nice objects to study. They contain an unambiguous quantity, which is this f I've spoken about. So one thing that you would like to compute is the partition function on the 3-sphere of this n equals 2 supersymmetric gauge theories. Okay? The partition function on the 3-sphere of a supersymmetric gauge theory is probably calculable. Even if you don't dive into the details, you can sort of imagine that the partition function is calculable. The intuition comes from the Witten index, for instance, who calculated the partition function on the 4 torus of a theory which was supersymmetric. So if you have enough supersymmetry, partition functions should be morally calculable, right? Even if the theory is strongly coupled. Because all the bosons and fermions cancel out, and you just remain with a finite number of propagating guys that you have to take into account. So the natural question to study, once you've established a supersymmetric theory on a curved space, is to ask what is the partition function of this theory, given that it's a supersymmetric theory. And this is why there is so much work going into studying supersymmetric theories on curved space, because one could then calculate their partition function, and this in principle gives a lot of new handles on the dynamics of supersymmetric theories in addition to the Witten index. Those of you who read a bit the literature of supersymmetry know that the Witten index played a very major role in the development of this field in the beginning, when people found, well, later people found ways to supersede what he has done, but in the beginning this was very important. So now these partition functions on curved manifolds are likely to play the same role. Now that people are studying how to put supersymmetric theories on curved manifolds, there will be many, many new results on the analogous to Witten's index, but now they contain, now these partition functions are non-trivial manifolds, not just the 4 torus or 3 torus. Now these partition functions will be calculated on curved manifolds in 4 dimensions and in 3 dimensions. So this is basically the big motivation behind this business, that this partition function could encompass a lot of interesting data. So how do you compute this partition function for a curved manifold? What is the general strategy? I'll just give you the general strategy, I'll tell you the answer, and I'll draw the consequences from this answer. There are lots of details here that I'm trying to skip, just to cut to the chase of this business. So to compute the partition function, you need to perform the path integral over the theory with this action, where the action is the action, for instance, I've given in the beginning. So you couldn't, of course, solve the path integral. The path integral is way too complicated to solve directly, and you need to somehow use supersymmetry wisely to calculate the path integral. This is where a procedure known as localization comes in. Localization is exactly what Witten did also in the 80s when he computed the partition function of the 4 torus. So the idea is that you add to this theory a new term, which is a commutator of Q with something else. And that's the basic idea. This is called localization, because if your Q squares to 0, and you can check that this transformation laws square to 0, so that's another thing that's important. You can check that doing the transformation twice on any field, it gives you exactly 0. So if you have a Q which squares to 0, or delta, whatever you want to call it, you can add it to the action without changing the partition function. So the partition function is independent of T, right? Because if the vacuum is supersymmetric, the independence of T is established by means of lowering this operator, and Q annihilates the vacuum from both sides. Okay? So the partition function is T independent, and in particular, you can calculate this partition function because it's T independent at infinite T. Infinite T is like a semi-classical limit. At infinite T, all that you care about are the saddle points of this anti-commutator. Okay? So it's so funny that eventually the partition function does not even depend on the original action to some extent. It only depends on the zeros or the saddle points of Q, comma V. And V you can choose judiciously. You can choose V to be whatever you want. V you can choose in some convenient way, such that the zeros of Q, comma V are nice and under control. Yes?
Delta squared to 0 on the field, but not on any operator, right?
No, in this convention that I've chosen, delta squared is 0 on all the fields, which means that it's 0 on all the fields. Which means that, so why? Let me just tell you why you need that, and you'll understand everything. The reason that you need delta squared to be 0 is that you need this action, S plus TQV, to be supersymmetric by itself. You don't want this to break supersymmetry. So you know that S is Q invariant, Q comma S is 0. So you just need to make sure that QQV is 0. Yeah. One easy way to make sure that QQV is 0 is to have a Q squared which vanishes on all the fields.
But I'm asking if it vanishes on all the fields, it doesn't vanish on all, V's, which can be composite operators. That's what I'm saying.
That's true. That's true.
You really need to check it for the V.
That's true. That's true. That's true. You need to make sure that Q squared annihilates all the local operators, which is true in the supersymmetry algebra. In this algebra, there is a delta, and there is a delta dagger, and you can prove that delta dagger is P, while you can prove that on all the other operators, delta is 0. This is like the definition of the SUSY algebra. So one easy way to ensure localization is to pick a delta which is 0 on all the operators, on all the local operators of the theory. So the meaning of localization, the physical input, is that you put this t, and you send t to infinity, and then you essentially forget, surprisingly, of the original action whatsoever. So the only thing you care about are the zeros of q comma v, and then the art in this business is choosing a nice v, a v that has a nice set of zeros that you can control and solve. In Witten's case, where he studied T4, he chose a v such that q comma v was in one-to-one correspondence with the space of flat connections. So it was an isolated set of points which you could account for. In these theories on the sphere, it's sometimes more complicated, and sometimes it's even easier. So there is a lot of art here of choosing v, and people managed to choose a v in this class of theories that I'm discussing, meaning n equals 2 theories on the sphere. People managed to find a v where the set of zeros is essentially trivial. You remain with absolutely nothing that is threatening or complicated technically. You remain with 1 point, basically, and you can do this path integral. One conclusion which is very important that you can draw without going into the computation, and this is what I want to emphasize, is that since the computation becomes completely independent of the original action S, it actually only depends on the Q guy. It only depends on Q and on V, and V you choose in some smart way. The fact that it depends only on Q's and V's allows you to draw a very important conclusion, which is that notice that in all the transformation laws that I've written, whenever you find a sigma, which is some background parameter in the theory, and whenever you find the R charge, they always appear in this fashion: sigma plus I sigma plus R, or minus R. So that gives rise to some mysterious holomorphy. So a mysterious holomorphy of the partition function when it's evaluated in the background of some gauge field and for some generic R charges. So the partition function turns out to be holomorphic in a, no, this is dead. The partition function turns out to be holomorphic in I sigma minus R. So this turns out to be just a function of I sigma minus R. So the partition function is calculable. And when you calculate this partition function via this localization, you also find that it's a holomorphic function. Okay? The fact that it's a holomorphic function means that it satisfies the Cauchy-Riemann equations. So the derivative of the partition function with respect to sigma is the same as the derivative of the partition function with respect to R. What is R? I should remind you that R is the choice of the R symmetry that you have made. There is one special choice of this R symmetry which corresponds to the physical R symmetry of the conformal theory, but you can choose any R. And you can compute this partition function for any R you want. Okay? Yes?
So if the original action was neglected, how can the result depend on these?
Oh, because the transformation laws depend on sigma and R. This is why it's holomorphic, because everything depends just on the transformation laws. Okay? So you should remember that sigma is some background parameter, which is physical. You can couple it to a certain operator in the theory, and it has a definite physical meaning. While R is a spurious quantity in some sense. It's the choice of the R charge that you've made before you started the computation. So now there is an argument, a quick argument, that relates this to what I've been discussing, to some monotonic property of the partition function, following from the Cauchy-Riemann equation, and the fact that these things satisfy the Laplace equation, essentially. So I'll go through this argument now quickly, and you'll see that to some extent, in n equals 2 theories, you can say a lot about this F theorem, this conjectured F theorem, from this holomorphy and localization, which is a whole technology by itself that I'm not going to teach very rigorously. So the argument is that Z3 satisfies the Cauchy-Riemann equation, meaning d sigma of Z3 times I equals minus dr Z3. I hope I didn't mess the sign. Small r. This is the R charge. Yeah, this is the small. Yeah, the notation in the file. This is the R charge. The radius of the sphere is just 1. Okay, given if if I did not mess the sign here, you get this Cauchy-Riemann equation. And now there is a nice physical argument that this actually must be 0 for the following reason. This sigma of Z3 corresponds, so sigma, you remember, is a background gauge field. You should think about it really as a background gauge field. So the first derivative of the partition function with respect to the background gauge field should vanish. Because if you're sitting, so this is 0 at the fixed point, I mean. So this is 0 when R is the superconformal R, and when sigma is 0. So it's 0 at the particular point, which corresponds to the physical conformal point. And the reason it's 0 is because this is a one-point function of a theory on a sphere, which by a stereographic map can be related to a one-point function of the theory in flat space. And in flat space, in a conformal field theory, all the one-point functions vanish just by dimensional analysis. So the derivative of the partition function with respect to sigma at the critical choice of the R charges, that's very important. It's not at every point. It's just at the critical point where R equals R star, where R star is the conformal choice, and at sigma equals to 0, this derivative is vanishing. What does that mean? It means that the partition function is stationary also with respect to changing the R charge at that point. The R charge, changing the R charge does not correspond to deforming the theory by an operator. Changing the R charge is some choice that you make before you put the theory in the sphere. But because of this holomorphy, this mysterious holomorphy, and because of the Cauchy-Riemann equation, the conclusion, which I'm going to put here, is that dr of a ZS3 at R equals R star is 0. What does it mean? It means that if you so physically, if you did not follow the details, you can forget about them now. I'll explain what that means physically. And this is all you should remember. So the idea is that you can take any n equals 2 theory with any choice you want for the R charges, and you can put it on the sphere. There is a formula for how to do that, and it's been worked out. It's also in the notes. There is one special choice for this R symmetry, which I call R star. This is the choice for which this theory can also be understood as a conformal image of the conformal theory in flat space. This is called R star. This is where the theory, this is the choice of the R symmetry that corresponds to the superconformal n equals 2 multiplet. What this equation means is that if you compute the partition function as a function of this choice of the R charge, it's stationary, it's extremized at the critical choice R star. Or in other words, if you do not know, the other way of interpreting this equation is that sometimes we do not know what is the correct choice of the R symmetry. Sometimes when the theory is strongly coupled, there is an R symmetry and there are many U1 symmetries, but we don't a priori know which of these R symmetries that we can form by combining one R symmetry with any U1 symmetry, we don't a priori know which of them is the superconformal R symmetry. This equation means, this is an algebraic equation because I told you these partition functions can be computed. So this algebraic equation allows you to find the correct choice of the R symmetry for which the theory is superconformal. Okay? So a simple example is this free scalar that I've shown you in the beginning. For the free scalar, the correct choice of the R symmetry is a half. We know that because we know that the critical dimension of a free scalar is a half in 3 dimensions. So there we know that the correct choice is a half, but you can actually check that if you compute the partition function without knowing what's the correct choice of the R symmetry, suppose you didn't know what's the dimension of the scalar, you would find that exactly at a half, this partition function is extremized.
There's one stationary point?
That's a stationary point. No, there are many. There are many. It's not true that it's the only stationary point. There are many. But that's already good enough because sometimes you have a perturbative point which you can deform continuously, and you know which is the correct extremum. So this is a semi-integral, well, this is a semi-algebraic equation. It's actually a matrix equation, which allows you in principle in theories where you don't know the R symmetry to fix the R symmetry. Now, it turns out, and of course this partition function is the partition function that I was discussing. This is F. This is the object, this is the partition function of the 3 sphere of this theory when compactified on a 3 sphere. Only here I'm studying the derivative of this partition function with respect to some auxiliary parameters. Now, people have studied this result in many examples. It's true in all the examples that people studied. And there is an empirical observation that has not been proven yet, and people have been working on it for a year or so. And what people found empirically is that the second derivative at this critical point is always positive. Well, in this convention of the log. So this is of the log, actually, and in this convention, this would be positive. So what people have found is that if you let this R charge vary, if you don't know what's the correct R symmetry, people have found empirically, so there is a typo in my notes in equation 2.3. There should have been a second derivative. So people found empirically, there is no argument for that yet, although many people have been working on it for a year or maybe more, that the second derivative is positive at the correct choice of the R symmetry. And this is where one can shed a lot of light on the F theorem. If you accept this fact, and if you accept this empirical fact, which is probably true because it works in tons of examples, but there is no formal argument for it yet. If you accept these two facts, I'll show you how you can almost prove this F theorem in supersymmetric gauge theories in 3 dimensions. N equals 2 supersymmetric gauge theories. Of course, you would like to prove the F theorem for any theory in 3 dimensions, but proving it for some class of N equals 2 theories in 3 dimensions is a good start. So from these two equations, I'll now explain you how this happens, how one can almost prove the F theorem for supersymmetric gauge theories. So the idea is that you consider some RG flow, again, from some UV CFT to some infrared CFT, where this RG flow is triggered by a relevant operator, like as usual. Okay? So we have a system which is N equals 2 supersymmetric. So this is of course N equals 2 supersymmetry. I'm discussing now N equals 2 supersymmetry in order to use these results. So you consider some N equals 2 supersymmetric theory, you consider some RG flow triggered by a relevant operator, and you flow to some infrared CFT. Now the partition function of this, now you can try to compare the partition function of the conformal field theory that describes the short distance physics, the ultraviolet physics, and you can compare that to the partition function that describes the infrared physics. Okay, you can compare these two quantities, these two z's, and this is of course the content of the F theorem, a comparison between these two partition functions. But now that you know that there is a space of parameters for which the partition function is maximized, well, the log of the partition function is maximized as a function of some parameters, which are these R charges. Okay. Now, under some favorable circumstances, if you start from a conformal field theory at short distances with some space of possible R charges, when you add a relevant operator, what it would do is to break some of these R charges, some of these R symmetries explicitly. Okay? So generally, this is a general rule. If you have any physical flow, this is a general rule that holds in many examples, not always, but it's a pretty good guideline. So if you have a physical theory at short distances with some number of symmetries, when you deform this theory and you flow to a new fixed point in the infrared, this new fixed point in the infrared will have less symmetries than the original number of symmetries of the UV fixed point. That's not always true. It's not a theorem. But for this class of theories, for which the number of symmetry just decreases along the flow, I can make a statement. So that's a class of theories which are supersymmetric, but it does not include all of them. This is true because basically, what is a flow? You add a relevant operator. A relevant operator would break some of the symmetries, and you'll flow to a new fixed point with the reduced number of symmetries. There could be new accidental symmetries of the infrared fixed point. That's an interesting phenomenon that takes place in many known examples. But in many examples, it does not take place. And for this set of examples, I'll make a statement. It's in this set of examples where there are no new accidental symmetries, the space of allowed R charges in the infrared is smaller than the space of allowed R charges in the UV, because there are less U1 symmetries in the infrared to mix with. Many of the U1 symmetries are broken by the relevant operators which trigger the flow. And then, because it's maximized, what you find is that in the infrared, the space over which this partition function is maximized is actually smaller when you maximize a function over a smaller set of parameters, the maximum will be lower than if you maximize this function over a larger set of parameters. So for a class, just to summarize, so for theories without accidental symmetries, so that's basically the only assumption I'm making. So for n equals 2 theories without accidental symmetries, of course, having no accidental symmetries is a strong assumption. We know it's violated in many cases, but it still holds in a pretty large and non-trivial set of examples, especially flows that are not very long, flows that terminate quite quickly. Then you would not have time to generate a new accidental symmetry. So for n equals 2 theories without accidental symmetries, we find that log of z in the infrared minus log of z in the infrared is smaller than minus log of z in the UV. Okay? So you see that for n equals 2 theories in 3 dimensions, if you assume that there are no accidental symmetries, one can make a pretty strong case for this F theorem.
And the case where the assumption doesn't hold, was it checked?
Yes, now of course, yes. Now cases where there are accidental symmetries have to be treated separately, because you understand, now I told you that basically this partition function is maximized over the space of global symmetries. So if you have an accidental symmetry, you have to take it into account. You have to
theorem still holds there?
Yes, so people check many examples and it still holds numerically, but there is no compelling argument for the general case. So if you have an accidental symmetry, you maximize this guy over one space of symmetries and this guy over another space of parameters, which are not visible in the UV. So you don't know a priori what's going to happen, but people check numerically and it's satisfied. For theories where there are no accidental symmetries, especially if the flow is short, then you don't have enough time for some strong dynamics to create a new accidental symmetry or a new free particle or something. Then this theorem basically carries over and you see that the F theorem is vindicated. So this example with the fermions, a supersymmetric version of this example with the fermions that I've started from, where you generate a Chern-Simons term, falls into this category perfectly well, and many other examples. So of course I couldn't build the whole formalism of supersymmetry in curved space, partly because it's not fully developed yet, and partly because it would anyway hinge on a result which is known to be true only empirically, that this extremum is always a local minimum, a local maximum, sorry, with a minus sign here. So this is not known to be a true result yet, but if you grant me that, then one can make a pretty strong case for this F theorem. Yes?
That argument can be for n equal 1 case?
Okay, n equals 1 case is an excellent question. For n equals 1, there isn't enough supersymmetry to localize the partition function. Yes, so you can write n equals 1 supersymmetric theories on a 3-sphere, but for n equals 1, there is only one supercharge, and when you square it, you don't get 0. You get a killing vector on the 3-sphere, and then it's much, much more complicated, and I don't think one can localize it. Basically, to get localization, you need the delta squared equals 0 guy. And when you have just one supercharge, you just cannot find an appropriate delta squared. N equals 2 and S4 perfectly good, can be localized. You can get tons of very interesting results for mathematical physics, Seiberg-Witten theory, Polyakov loops, 't Hooft loops, whatever. It's very interesting. Yes.
One step when you go to the sphere theory, many ones, many choices.
Yes.
It's clear that if you have the conformal case, then the first two are the best bet. If you're looking at that fast, what guarantees you that you can go the other way? If you find a point in some application of U1, right, which is a critical point, is that sure that it's super conformal?
I think, just tell me if I understood the question correctly. You're asking, since this extremum is not unique, you're asking whether there could be some phase transitions, that I would somehow follow the same extremum, but I'll be misled. That's indeed the worry, that if you want, this should be stipulated among this was one of the stipulations of the theorem, that there are no funny phase transitions in the extrema. But I think that in all the known examples that people studied, this was actually not just a local maximum, but a global maximum. And then it goes away, the worry.
So in all cases,
all cases that I've looked at, I mean, there are by now thousands of them. I looked at a few, and in that case, it was also a global maximum. So if it's a global maximum, then your worry goes away. If it's just a local maximum, then there could be funny phase transitions. There could be many maxima, and you could land on the wrong one accidentally. And then this should be among the stipulations of this argument. So it's a pretty strong case for the F theorem. For some class of theories, it's by far not convincing. There are many holes, but this is the state of the art, and it's a very interesting problem on which many people are working. Yes?
The outcome of the localization is necessarily non-divergent because you didn't...
Oh, divergence, okay. Yes, so you can prove that's something that's not, well, you can prove that the first derivative is finite, non-divergent, and you can prove that the second derivative is finite and non-divergent. Z is divergent. But all you need for this argument is the derivatives. Z is divergent because, well, it has this Einstein-Hilbert and the cosmological constant counter terms. So these are some power divergences that you can remove. They do not affect F. But you can prove that the first derivative of Z is actually completely finite. There is no counter term for the first derivative of Z. Okay. Okay, so that basically finishes what I wanted to say about 3 dimensions. Yes?
Sorry to insist, but I'm still confused. Don't grasp well the Chern-Simons issue.
Okay, that's interesting, yes.
Let's take the fermions with one mass, with the positive mass.
Positive sign.
Okay. Now you integrate out.
Yes.
And you say that in the infrared you get a non-trivial result, which doesn't reflect C equals 0, which you would expect because these guys are decoupled. So you would expect to see no trace of them.
Yes.
And nevertheless, there is a trace which actually can be very large.
It's a topological guy.
So this is somehow a trace that these things don't decouple?
No,
or
any field theorist would say that there are no degrees of freedom in the infrared. The infrared is what we would call an empty theory.
Okay,
The infrared is an empty theory from the point of view of degrees of freedom, but it's non-empty from the point of view of some funny gauge configurations on the sphere. So there is a space of vacua which is parameterized by the flat connections on the sphere.
Okay, but now my intuition, which goes wrong, I guess because of the thing that you also have negative Fs, is let's add the other more fermions, the
Yes.
ones with the opposite side.
Yes.
So in the infrared, even though you added more stuff,
Yes.
so you would guess maybe the system has more memory after you integrate it out, it actually looks even better because now you don't have the Chern sign.
That's right. That's right.
So
It cancels.
I added more stuff, which
Yes. Yes.
is should
Yes.
be remembered.
So that only shows you that it's not anything to be remembered. It's not something about remembering. It's not that the system in the infrared, the conformal field theory in the infrared is empty. It doesn't care where it came from. It just depends on the level. And that's it. I don't think what one can force yourself. Yeah, it's.
Why is it so surprising? I mean, it really isn't surprising. Remember, see, the number of degrees of freedom of quantum filter, propagated degrees of freedom is really infinite. There's divergence, volume, and portion of volume in your Z and everything. You're looking at the finite piece remaining.
Yes, but
Which is some characterization of the number of degrees of freedom, all right. But it's, it's not what we would call the number of oscillators that make up the quantum field theory. And in a topological theory, Chern-Simons theory, you presumably you don't get those
Yes, yes.
dependent pieces. You get just a finite piece.
That's right.
Characterizing indeed the
Yeah, I guess when.
multiplicity of states in the vacuum.
Yeah, I guess when one says degrees of freedom, one means their free energy density or something like that intuitively.
No, but you're not. No, you're calculating
This partition function.
everything. And
This is why the Chern-Simons term is surprising. Yes. It's surprising in the sense that a cosmologist would not assign any number of degrees of freedom to a Chern-Simons term. So if we lived in 3 dimensions,
He wouldn't care about finite number of degrees of freedom.
yes, exactly. This is why you should not assign, you would not assign any number to them intuitively. It's a discrete set of solutions, and counting them as a degree of freedom, counting them on the same, let me put it this way. Counting a Chern-Simons term on the same footing as you count a propagating scalar, and sometimes it gives even a larger contribution, is funny.
And I presume, based on your first talk, you're going to come out the entropy, and then it's clear that this theory like this has entropy.
Yes.
In the graph state.
Yes.
T equals 0.
Yes. Yes.
So if this is related not to,
Exactly.
More to entropy than to energy.
Mm-hmm.
It's not at all surprising.
Mm-hmm. That's right. That's right. So in the next talk, so basically this is I have 5 minutes for questions. Yes. Huh? Yes. The plan for the next talk would be 4 dimensions and then information theory, a bit entanglement entropy, information theory, and the connections of all these ideas to entanglement entropy. Yes. The what?
Suppose this F theorem is correct.
Yes.
That it has application to solid state physics. What
Yes.
about the application?
Well, solid states physicists are extremely interested in this theory of U1 QED with an F fermions. This is a theory that interests them a lot. There are many papers about this theory in solid state physics. There is a story with 2 fixed points that merge. There is a whole story there. And having such a theorem constrains the dynamics. Simply constrains the dynamics. It constrains what can be, they're interested to know what is the infrared physics of Chern-Simons theory with an F Dirac fermions. I've shown you that in their perturbative regime, it's consistent with the F theorem. But they're interested to know whether this theory can spit out the degrees of freedom that they're interested in. They want to see some, their excitations there. Something like, well, they want to see some quasi-particles emerging and so on and so forth. So once you have an inequality, it's almost on the same footing as a 't Hooft anomaly matching, only not dimensions. It constrains the possible outcomes. No, they don't know about it. This F theorem did not yet creep into condensed matter. No, but that doesn't matter. This is a constraint to the dynamics in flat space, because once you have a conformal filter in the infrared in flat space, you can calculate F. So this is why it's interesting, because it gives constraints on the dynamics of the theory in flat space. Even though I'm using a compact sphere for some calculations, it gives constraints on flat space. So, having constraints on the dynamics of quantum field theory in flat space, which are not supersymmetric, is interesting, and it's important. Even if not to build a bridge, maybe, conceptually it's important.
That's something to be checked experimentally.
I don't know whether they're even aware of that yet. So. Yes. Yeah.
For another question, our Chern-Simons case, you got one over 2 row K U1 Chern-Simons partition function.
Yes, a half log K.
And what is the space? S3, or you integrate out some M? So
Yes, M is said to be S3.
S3.
The partition function of the Chern-Simons theory without supersymmetry is known for any manifold. It's basically, this is what Witten did in his paper on Jones polynomials.
M is just S3?
Yes, I quoted the result for a S3 sphere. You can find them, you can read them out, you can find them in Witten's paper, basically. I just copied.
So what other manifolds have been calculated?
Okay, that's a great question. Of course, there are boring orbifolds that people have done. People have also found, rather surprisingly, that this S3 sphere admits a squeezing. So you can take the S2 fiber, you can think about it as an S2 fibered over an interval, and then you can think about this, you can modify the fiber. So you can squeeze the S3 in various directions, and it surprisingly still admits localization. So you can squeeze the S2, you can orbifold it. I think there are 2 different squeezings. As far as I remember, there are 2 different squeezings, which are inequivalent. And that's what I think has been done so far in 3 dimensions. But I know for sure that people have not discovered all the manifolds and they've not exhausted this field. There are many people here who are, there are some people here in the audience who are working on that, and they tell me that there is a lot of progress in this field. So, okay. Any other questions? Okay.